great pleasure to be here. So maybe I'll just begin by say a little words about the motivation of my talk. I need a chalk. Okay. So, of course, the very big motivation of my work is from this homological mirror symmetry for non-compact manifolds, in particular for those log Calabi-Yaos arising as under-canonical divisor complements. So is the writing good?
Maybe deeper.
Oh, sorry. So it motivates us to ask the question whether this general conjecture is itself functorial, in that from a symplectic geometry point of view, there's a similar functoriality property that are mirror to that in algebraic geometry, which are themselves realized as Fourier-Mackay transforms. But first of all, let's review what these functors are from algebraic geometry, at least basic properties. Suppose you have two, say, typically affine manifolds, and you want to consider derived. So these are affine. So you want to consider the derived category coherent sheaves on them. And suppose you have a map, a morphism, or even more generally a correspondence between them. So you want to ask, under what conditions does this morphism induce a functor between their derived categories? But so the very simple condition says the F has to be proper in order for it to induce a morphism in this way. So due to the result by Grothendieck and Grau, it says the pullback is always a coherent, but not for the push forward. And we'll see that in symplectic geometry, the correct notion of such morphisms are typically given by Lagrange correspondences. So in a similar picture as in algebraic geometry, we'll see that such a notion of morphism can be generalized to a coherent sheaf on the product. So F is in a coherent sheaf on X across Y. So for it to define a Fourier-Mackay transform, you need that, say, up to derived equivalence, this suppose F is equivalent to structure sheaf or subvariety, where S is the subvariety of X cross Y, then the correct notion for this properness condition is that S to Y should be proper. So such a restrictive condition is somewhat different from the case of compact manifolds, where you don't in fact require such things because everything is compact. Okay. So in a similar nature, you want consider Lagrange correspondences between your non-compact manifolds. So today we're going to talk about Calabi-Yau manifolds and Lagrange correspondences between them. But not all Lagrange correspondences will give rise to functors between the rough categories, as we've seen, but we'll seek for geometric conditions on such Lagrange correspondences for which they really induce functors. And in fact, such conditions are simple. Let's say the very first condition as an analog to this algebra geometric picture is that an Lagrange correspondence from X to Y should satisfy condition 1. that a simple condition that this natural map to Y is but of course this cannot be enough, because defining the rough categories themselves are complicated enough. You must have further geometric conditions on Lagrangian submanifolds of these Stonybrook manifolds in order for the rough Fuller theories to be well defined. Okay, so let's go directly to the story of rough categories. I'm not sure if I'm writing it bigger, but it looks like the same size. Anyway, so as we just mentioned, we'll be considering Liouville manifolds. So these are pairs M and lambda M. Well, M is a non-compact 2n-dimensional manifold, and lambda M is a so-called Liouville form. Maybe I also specify this Liouville vector field. So Liouville, and well, for simplicity, we'll be working with those satisfying this Calabi-Yau condition, C1 of M equals 0. For both for the grading reason and in fact, we'll be interested in only examples where these are, for example, they're divisor complements of anti-canonical divisor of a monotone, compact monotone manifold. So that would be Calabi-Yau. And for such manifolds, homomirror symmetry has itself a clean statement. Okay, so this condition, and so its rough category. As you all know, that the object, so we're defining an infinity category W of M, whose objects are so-called exact cylindrical Lagrangians. Which means that exactness means that there's a function on this whose differential is this one form, and cylindrical means that outside of a compact set is invariant under the flow of Z. And the infinite structures that the morphism spaces between a pair is this. So to define morphism and so on infinite structures, you also have to specify a correct chain model for the rough flow complexes. So there are, of course, different ways of doing that. For example, you could take a cofinite family of linear Hamiltonians and take a direct limit over this. And we also could use a single quadratic Hamiltonian and simply define this rough flow complex with respect to that Hamiltonian. Or you could take abstractly take over all positive isotopies of your Lagrangian and take direct limit over that system. But for convenience, we'll be working with, this rough category is defined by choosing a single quadratic Hamiltonian. Let's call it H, depending on M. So this quadratic means that in this cylindrical end of this, this function only depends on the radial coordinate and is r squared. So then this rough Fuller complex of a pair is, of course, by definition, this Floer-Cauchy space of these Lagrangians with respect to this chosen Hamiltonian. Assuming that this is non-degenerate, and so A-infinity structures similarly, by considering inhomogeneous homomorphic disks where this inhomogeneous term are given by Hamiltonian vector fields of this Hamiltonian, where in fact, for technical reasons, we'll work with a time-independent Hamiltonian here. Okay. Defined by okay. So the drawback of this is that defining the radical category in this setting really depends on the choice of Hamiltonian with a specific behavior and infinity. So that gives rise to some ambiguity when you talk about the product manifold, because you want to relate different manifolds. So when you consider product manifold, it has a natural Liouville structure with respect to the direct sum, or maybe direct product of these forms. So lambda m cross and lambda n has a natural Liouville structure. But there are two kinds of natural choices for Hamiltonians for which you realize such Floer complexes. So it's very easy to make a picture, but for Hamiltonians, there are two choices. One is H1, it's so-called split. It's natural to take the sum of pullbacks of Hamiltonians on factors. So and the other choice is defined as follows. So your Liouville manifold are just completion of Liouville domains, where you just, this completion picture can be seen using this Liouville flow as the expanding flows of a symplectic manifold. So when you consider the product of the Liouville domains, you get a hypersurface with corners. Then you choose a smoothing of that. And then you reparameterize this non-compact part by using this Liouville structure. Then you get a new cylindrical end. Let's call this hypersurface sigma. And then the cylindrical end for this product is sigma times 1 to plus infinity. So this, let's call this. And you can define a Hamiltonian which, outside of this compact set, only depends on that new radial coordinate you have. Let's call it radial. So, okay. Then you attempt to define radical categories with respect to these two kinds of Hamiltonians. A priori, in fact, they should have different objects. So for this, it is natural to, so defining radical categories these will naturally include objects like products, L times M prime, where L is in the exact cylindrical Lagrangian in M, and L prime is 1 in N. And for these, you can have all sorts of Lagrangians that are eventually invariant in this radial direction. So these are cylindrical. But in fact, both kinds of Lagrangians are cylindrical in the sense that they're in fact cylindrical with respect to the same Liouville structure. So we wonder whether they can be defined as objects of the rough Fukaya categories of both kinds of Hamiltonians. So that's the first thing, the first result I got. So maybe it's proposition or theorem, doesn't matter. So it's so you can have both kinds of Lagrangians have well defined Raphler theory with respect to either H1 or H2. Okay, and furthermore, so maybe it's better to call it a theorem. The furthermore is says, in fact, such a structure does not depend on the specific way where you choose your perturbations larger than infinity to define this notion of Raphler theory. So it says there is a natural functor from the Raphler Fukaya category defined with respect to H1 to that defined with respect to H2, which is a quasi-equivalence. Okay. If the yes.
Rescaling trick make splitting into a radial.
That's correct. That's the basic idea. Yes. And that also explains why both kinds of objects can be included. But this, if time permits, I will explain more. But let's say, so the idea of this, maybe it's not a very big, is that it's not defined in a single step. Of course, it's not a correspondence functor, but it's defined as a homotopy direct limit of some system like this. So if starting with the H1, so which is Hamiltonian, which grows like this, and your Lagrangian is conical like this, then when you define these Floer complexes, because these Lagrangians are exact, there's a natural notion of action of generators, which are Hamiltonian chords, time 1 Hamiltonian chords for this Hamiltonian from L0 to L1. So using that action, it defines a filtration on this Raphler complexes. To say that more precisely, you must estimate the primitives of your the chosen primitives of your Lagrangians, but you can choose your primitives helpfully so that this notion of action really defines the filtration. Then you fix some action filtration window for your Raphler complex, and then you can choose a large enough compact domain inside your product manifold for which all the Hamiltonian chords within that action filtration window are contained in this large compact set. And moreover, it has the property that any holomorphic strips between them, or more generally infinite disks, will not escape this region. And so given that, you just slightly modify this Hamiltonian outside of this compact set to something which is radial in this radial function, radial coordinate. And because of that, you have a map from this truncated fluid complex defined with respect to H1 to some subcomplex of a Hamiltonian which looks like H2 outside of a compact set. So you have some fluid complex truncated to, in fact, it's also a truncated fluid complex with respect to some Hamiltonian, let's call it that H of B, where this truncation depends on B. In fact, is a form minus B to some A. Where you just restrict your generators to the corresponding generators because the Hamiltonians are the same inside this compact set. So this HB has the property that outside an even bigger compact set, let's say R greater than or equal to some capital B depending on B, this HB, some other coefficient A depending on B, R squared, where R is that radial coordinate. And then you compose this by rescaling to reduce this to some Hamiltonian which is only R squared. So, and use a compact supported deformation of that resulting Hamiltonian to one that you have chosen to be your H2. But that's completely flexible. So that's the usual continuation map with respect to a compact supported isotope deformation. Okay, to get something like this. Once you get this, then what you need to prove is that such a diagram is compatible with natural inclusions of maps, but of subcomplexes with respect to action filtrations. But that can be analyzed in a straightforward way. So for instance, you choose some sequence of numbers going infinity as you multiply to this lower action bound. And in fact, such a diagram in fact commutes up to chain homotopy. Well, this chain homotopy can be found explicitly when you trace along these rescaling maps and continuation maps. Okay. And the higher order maps are defined in a similar way, where you arrange so you have tensor products of such things, and suppose you're given a finite collection of Lagrangians for which you can fix a common lower bound of the action of the minimal Hamiltonian chord. Then you choose your lower action bound depending on your given inputs and arrange them in a compatible system. It's a bit vague here. The idea is that you work among a finite collection of Lagrangians for which you can arrange these numbers, and then you draw a diagram like this and trace along these rescaling and continuation maps. You'll find the diagram which is commutative up to homotopy. Then you take homotopy direct limit that's this functor. Okay. So the consequence of this small proposition is you have a well-defined meaning of Fukaya of the product manifold. So that's the next. So you can say about this next condition on your Lagrangian correspondence, which is that you want to look at Lagrangian correspondence L, which itself is an object of the product manifold M minus cross N. So such Lagrangian correspondence itself has a fuller theoretic meaning. So then you expect it can be a functor can be associated it. So geometrically speaking, it's some Lagrangian like this, or it's a product. But given this, in order for it to induce a functor, this cannot be for example, cannot be a product of two non-compact cylindrical Lagrangians. You will see why. That's related to the fact that some modules of non-proper infinite categories are not representable. So we'll seek for constructions of functors. So that's in fact quoted Fuller theory study. Say the idea is due to. By the way, such an idea is originally due to Wansha when he studies the Kuhn's formula for symplectic homology, but we just slightly improve it and apply it to infinite structures. So construction of functors. So idea is basically quoted Fuller theory, considered by various people, which I name here. Unfortunately, Nate is not here, but yeah, Botman, Mao, Weinheim, Whitwood, and also another group, Fukaya, Lakili, and they also use the work of Lakili Piansky. Sorry. Okay. So in fact, the beginning step is for any object here, you can associate to it a bimodule over the Fukaya of the factors. So given now, it defines a bimodule. Let's call it P. How? It's a bimodule over this pair. So this notation is a bit confusing. I call it a right Fukaya of M and left Fukaya of M bimodule. Although I write this on the left, it's just the reason is for some Fuller theoretic reasons related to orientations of moduli spaces. So this is right structure here and left structure here. Okay, so the construction is simple. You just consider, instead of the usual infinite disks, you consider quoted surfaces which are generalizations of holomorphic disks like this. So we'll be looking at pairs of maps from this pairs of domains where they match on this Lagrangian corresponds L in the intermediate seam. And so here are your testing objects for your bimodule. And so these are flow cochains in M, and those are flow cochains in N. And these are module inputs and outputs. So this is a simple construction. So by a simple homological algebra, you can turn it into a functor like this. Such a thing defines a functor, series B, infinity functor from the reciprocator of M to left modules over the reciprocator of N, where this functor is in fact contravariant. All right. So, but this thing is in fact too large. You have a non-proper infinity category and consider all left modules of it. There can be many complicated modules which are far beyond comprehension. So the natural question is, how do you produce a very geometric functor from that to the reciprocator itself? So that of course for that of course you have to use this condition in a suitable way, and that question can be phrased as the representability problem for this module valued functor. Let's see. So the question is, does there exist a functor, say from reciprocator of M to that of N, it's called, maybe called theta, such that phi of L is homotopic to theta of L composed with the left Yoneda functor. So this is left Yoneda, which itself is, so left Yoneda functors are contravariant, so you compose to get a, so this is covariant in fact. All right, so this is the way we're going to obtain such a functor, and the answer is not always the case. For that purpose, you have to slightly modify these reciprocators themselves. Okay. What time is it? All right. So.
By the way, you can use both lower and upper.
Hmm?
You can shift.
Oh, really? Sorry. Yeah. Maybe I'll finish this part and good. So, not always. For instance, to achieve this, need a slightly improved notion of the reciprocal category. Which is basically none to everybody here. So these are, first of all, you have to appropriately complete these replications over the Novikov ring. For that purpose, you need to consider the following thing. So let C be your Fuller complex. I just denote for by C. Is any Fuller complex? It's over Z. And I consider this lambda vector. No, it's not a vector space. It's a free lambda module by tensoring over Z with the Novikov ring. So these. So lambda is a sum of this form. So this is sums, this form, finite sums. Sorry, finite AXI t to the power of lambda I. Lambda I goes to infinity. And then you complete it with respect to the following filtration. So F lambda is a filtration on this. F is a filtration on this algebraic tensor product such that F lambda is defined to be all those sums without finiteness. So the filtration has finiteness, sorry, such that the following thing is bigger than lambda. So it's minimum among all those AXIs non-zero, such that the action of that Hamiltonian called XI plus this lambda I, its exponent is greater than lambda. Equals, sorry. Okay.
In what sense the first one is finite?
Oh, it's a finite. It's just by definition tensor product.
But
Then what's the,
lambda I
then
was
I goes to infinity condition.
Oh, sorry, no, not yet. Not yet, sorry. So eventually I want this quantity to go to infinity after completion. Sorry, yeah, my fault. So these AXIs are some element in this orientation line. In the vector space generated by two orientations of the orientation line of xi. But let's just think of it as a Hamiltonian chord. So we have this. Then you have C hat is the completion with respect to F. And in fact, you want, for technical reasons, you want something over lambda 0, so let's C hat 0 is F0 of C hat. So such Flow complexes or Flow coaching spaces have infinite series where the exponent itself might not always be non-negative. They can have negative powers, but the requirement is sum of the action of that corresponding Hamiltonian chord plus that exponent is always non-negative, and has a natural induced lambda 0 module structure. All right. Should I push it up? So that's one thing you need to do. And the other thing is that, so in fact, the attempt to proving representability uses geometric construction of compositions of Lagrangian correspondences, which has been considered for many years. So suppose you have some object, replicative of M, and also correspondence from M to N. Then the composition is the fiber product over the diagonal inside of M cross M minus. So this composition is the map from the fiber product to N. So this is a notion, and that really means the map. So I want such things to have some nice geometric behavior. So that's another assumption. Condition, maybe I call it condition 3, which can be done in terms of the Fur theory in M. So when defining the Raphel category, you consider only, for example, a countable collection of Lagrangian submanifolds. Because in general, abstractly speaking, it is hard to arrange those perturbations in a coherent way when consider all kinds of Lagrangians. But it is possible for a countable collection of objects. So you consider, consider a countable, collection of Lagrangians in M, making up the Fukaya category, such that the geometric transform, the composition is cleanly immersed and cylindrical in the following sense. So
In what sense do you have diagonal M here?
on what?
The diagonal of M, where it's...
So okay, let me write this set theoretically. A set of points. So this is a smooth submanifold of this triple product. And this is a set of points P, Q, such that P is an L and PQ is on curly L. Okay. Yeah, I mean it's only a subset, but up to small perturbation, I can range that so it's a smooth submanifold. And this condition requires that my Lagrangian chosen from this collection has nice composition with this Lagrangian correspondence. And the sense of cylindrical means the following thing. So let's call this map iota. I want iota is an immersion of something like this, finite copies of some cylindrical Lagrangian modeled over Legendre submanifold So L is the Lagrangian in the boundary. Okay. So this finiteness is important. That's also reflect the properness condition. You don't want something. You don't want infinite many copies of your cylindrical end to map to a single piece, because that won't have a well-defined infinity structure. Although it can be regarded as an infinite rank module over your category. Okay. So basically, then, so given this, you'll see that typically such compositions are not a proper embedding, so you must, in a general case, you have to consider such immersions as objects. But in general, these might not be objects. For example, you have this kind of Lagrangians immersed in your manifold. This won't be an object, so the correct notion to have is first you define a curve in infinite category, and then you find solutions to a Maurer-Cartan equation for that curve in infinite structure. Then the objects in the new category will be pairs, where you have an immersion like this, and also an abstract speaking, a Maurer-Cartan element in a higher energy part of that null covering. So maybe I write something down. So by the way, so we need an immersed category so objects are pairs where iota together with some b, or b is a Maurer-Cartan solution. This is a Lagrangian immersion with clean self-intersections, where all self-intersections are contained in a complex part, and in a cylindrical end it behaves like this. It's a immersion of finite copies of something modeled over Lagrangian submanifold. And okay, and this because of time, I won't have time to explain all details, but the Fuller complexes are chosen. Fuller complexes are built up of a model where you choose a Morse function on the self-private product of this map, together with all Hamiltonian chords which are located in a cylindrical end from such L to itself. But for each copy of such pre-image, for each pair of copy, you consider a copy of that Hamiltonian chord. So you get a matrix value, something like a matrix valued thing in your morphism space. That's, so you have some C of iota 1, I0, B0. And it's defined over lambda 0. Okay. And so the main proposition is that, so denoted by hat inverse, is that if all these conditions 1 to 3 are satisfied, so conditions 1, 2, 3, then they exist a filtered infinity functor from theta hat from the completed version of Fukaya of M to this immersed category. Well, on the level of objects, is sent L to its geometric composition with curly L together with a unique bounding cochain determined by L and curly L themselves, representing this phi. And this, so in the last 10 minutes, I just want to briefly say what the underlying idea of this is. So, slightly different from what Nate side, well, Wanham Wood and also later done by Nate. The shrinking idea, which gives an isomorphism between the replica homology of this quoted replica complex and also the replica complex for this geometric composition. It's in fact a homotopy method where you kind of use the advantage of this flexibility in defining replica category, because everything is well defined up to quasi-equivalence. So idea is homotopy method. It was the Fukaya, Arcadia, Lipinski's original idea is, so we're going to define a homotopy from this module to that for any L, and this module where this is in fact, this is just sorry, how do you say it? From the I just like this to this to the Yoneda module associated to this object. Well, this B can be found in a same argument. So these are two modules over the replicative of N, and we're going to define this. So such a homotopy can be defined using moduli basis of quoted maps in a slightly complicated kind, where, say, it's this first term is in fact simple. You have such quoted maps well, I have to explain these conditions. So here's a given Lagrangian of M, and these are testing objects of your module. And here's some condition I have to explain later. So here, this is the module input of this module, and here is the module output for this Yoneda module here. And this condition, so here, this boundary condition is the geometric transform composition. Sorry. So this condition is specified to be some element called E. Well, this E is a unique element which corresponds to the homotopy unit in a self-Foucault chain space of this Lagrangian inversion. And involving this bounding cochain B, you also want to break this boundary into several pieces and impose that bounding cochain B on these arbitrary many times actual, and you sum over all of them. It's kind of complicated. And then more generally, this module, because you want this. Oh, sorry. Just a reminder, I have 5 minutes. In general, you want this module homotopy, this homotopy modules to be compatible with infinite structures in M. You also break this boundary into pieces where you put Lagrangian submanifolds in M, and those are given inputs of flow cochains in M. Okay. So this is the crucial condition where it really is a homotopy instead of just a morphism, pre-homomorphism equivalence. Sorry. And the idea is that it achieves the largest action in that flow complex. Well, if you order these generators according to the action, this map will be some upper triangular matrix, so that when you complete it over lambda, you will see that's an isomorphism. All right. So in the last 5 minutes, I just want to say briefly, because there are a lot of things which unfortunately I cannot complete. So this is a general abstract nonsense, but in many favorable geometric cases, we don't have to consider all kinds of Lagrangian immersions. We have nice Lagrangian correspondences in which the compositions are in fact properly embedded. So in those cases, we can pass back to the usual notion of Fukaya category, and we don't have to use virtual techniques realizing such virtual fundamental chains on the East moduli spaces. So one example, and it's in fact to my interest, example is that it's related in some way to this restriction map, where suppose you have a level subdomain U0 containing M0, and therefore it induces a map from U to M, where U is a convolution of U0 and M is that of M0, that's denoted by I. So you have a graph correspondence, which is the graph of I. Gamma is graph of I. So this satisfies the condition that this natural map from gamma to U is proper, so that you have a map from the replicator of M to the immersed replicator of U. But if you restrict yourself to Lagrangians which satisfies the condition that so if L satisfies the same conditions as the Viterbo restriction map, the strong exactness condition, if some of you might know. And moreover, L is invariant in this compact Liouville cobordism under the flow of M. Then we'll see that the geometric transform is just the restriction of L to U0, and complete that with respect to the induced Liouville structure on U. In that regard, you get, so starting with a subcategory, you get to a subcategory of an immersed category, which is in fact equivalent to the subcategory of embedded Lagrangians. And so one thing and proof is that in fact this is not too different from this Viterbo map. So this linear restriction morphism is in fact chain homotopic to this functor I just defined, to the linear morphism of this functor I just defined. So although this condition is somewhat restrictive, you will see, for example, I just finished now, but I say you'll see the main example of these are Weinstein cobalt system, Weinstein manifolds, and then the submanifolds, and these are, for example, stable and unstable manifolds of Lyapunov function. And you will expect those generate the rough Fukaya categories for which you have such functors realized in an ordinary sense. Probably I stop here.